So, hello everyone to our new meeting, our weekly meeting. We have two presentations today. One from
Essa live da Letícia, não era dele, não.
da Letícia. Vai ter que ser Letícia.
É,
Você deixa assim. Tá bom. Você.
é porque tem duas lives, essa daí já colocou o título, que é o teu.
Tá. So, hello everyone. Welcome to our weekly meeting. Today we're going to have two presentations. The first one will be given by Leticia. She will be talking about the Doubly charges Scalar at high luminosity and high energy LHC. So let's see what she has to say to us.
So, good afternoon, everyone. Let me. Is it sharing the screen? Yes. Okay, so as Andres said, I'm going to present this paper that, in fact, as you can see, is a previous paper of the group made by Farinaldo, Yoxara, and Tessio, which are previous students of Farinaldo. So basically what this paper does is put array scaling on an Atlas and CMS analysis for the bounds for a doubly charged scalar. This paper treats it in a non-dependent model way. So it made very simple assumptions, because the point of this paper is to get the lower bounds and not exactly like see the implications of different processes and different models. And the introduction, it says exactly this, because the doubly charged scalar, it's present in a variety of models, like the left-right, 2T1, the type 2 seesaw, and many others. And in many models, as well, in many of these models, it is treated to decay mostly in leptons, charged leptons. So having this in mind, it is not... it is okay to say, for us to consider, that the branching ratio can be 100% in leptons for, as I said, a non-model dependent analysis. So the goal of this is because, Atlas and CMS collaborations put out papers deriving these bounds for the mass of the doubly charged scalar, but there would be some upgrades in the LHC, like the high luminosity and high energy LHC. So they were looking for to put rescaling of the bounds. Like, sorry if I sometimes forget the words in Portuguese and in English. Okay, so as you can see, they considered the scenarios with 13 TeV center of mass energy, which is the one considered in Atlas, and then 14 TeV and 27 TeV, and there were also, here you can see better, these were the cases that were considered. So this case where the energy, center of mass energy, is 13 TeV, and the luminosity is 36 point, I don't think you can see here, but here is 36.1. This is the analysis made by Atlas. But in this paper, they in fact reproduce this analysis. So this curve is in agreement with the Atlas result. And then they rescaled for a different luminosity. So the process that is mainly considered is this one, the Dry-Young process, where a gauge boson, like a photon or a Z, is producing leptons in the final final state. Thank you. And these leptons are produced by the doubly charged scalars that are commonly considered like doubly charged Higgses. One important thing is that this came from triplet, which is considered triplet scalar, which is considered in many models as well, like the type 2 seesaw and left right. And by considering it and considering also this type of process, the resonant process, we can take the narrow wave approximation that is also essential for the rescaling of the bounds. Because considering narrow wave approximation and a resonant process like this one, we can rescale these bounds, not caring so much about the new collider backgrounds, because as we rescale, we are looking for getting these bounds for a new set of parameters, like a new luminosity, a new energy, center of mass energy, and also a new environment itself. So, but considering that this is a resonant process and narrow approximation, the background of this process is also a process like this. For example, if we produce two Z's here, we could have two charged leptons, but this would be minus and a plus, minus and a plus. But as we have mischarged identification, so sometimes an electron or muon can be misinterpreted as the opposite sign. So the ZZ channel also is a background. But what matters here is that the background is in a similar type of process as the signal. So the dependence of the cross section in the energy would be similar to both signal and background. That being said, the number of events won't, the ratio of the number of events of signal and background won't change as much as we have, is not here, but I will put just in the board. As we have this consideration. The number of events is proportional to the cross section and the luminosity, the degree of luminosity. So if the cross section of both signal and background changes similarly with the energy and the luminosity, the luminosity depends, but if it changes similarly with the energy, the number of backgrounds will also similar. The number of events will also change similarly, so we don't have to reconsider all of the new things of the accelerator or the collider. Okay, so given this, as I said in this paper, they reproduced first the atlas result, which results in this first graph here. In this graph, this black line is a theoretical bound. This curve in green, solid green, is the atlas that they derived, and assuming this also green one is for the same center of mass energy but different luminosity, 139 femtobards, inverse femtobards. So as you can see, what I said earlier implies that they both have similar shapes, very similar shapes. Okay, so with this, we can now get the lower bound for the mass, considering different types of branching ratios. So I think it's here. Okay, in this graph, they considered the branching ratio of the doubly charged scalar in electrons to be 30%, in muons 40%, and in muon electron 30%. But we can also change this percentages to be in 100% in electrons, then 100% in muons, or 100% in this channel, which is a lepton flavor violation channel. So assuming this, here we have this graph that shows the minimal bounds for the mass. Let me zoom a little bit. So this is the case where we saw the previous graph, same case, same scenario. 13 TeV, center of mass, and 139 inverse femtobarns of luminosity. And these numbers here is the minimal, the lower bound for the mass for each case. So in the previous one, we had 40% for muons, I think, and 30% going into electrons. So let's get here. Like it would be this one, 1.1 TeV, because this is in GeV. And if we get to the previous graph, so this would be this point where the black line meets the traced green line here. So 1,140. So they didn't put all of the graphs for the cross section here, but is by this strategy that we get all of these lower bounds here, depending on the branching ratio. One thing that we can see here is that if we go to 100% in electron and 0 in muon, we see that we have lower bounds on the mass than comparing to 100% in muon. And this happens to all of the scenarios, the case scenarios. There's because the mischarged identification is much more preeminent in electrons than from the muon's case. So in the case of when it decays only in muons, we don't have this problem in the background as much, the misidentification of the signal. And as you can see, it impacts very much on the bounds. But a good thing is that I don't know much about it, but it is a reducible signal, so it can be improved in the case of the misidentification. But if we go to 0% in muon as well, 0% in muon and electron, we also have stronger bounds, so in higher mass, and that is because the signal here would be the doubly charged going in muon and electron, which is lepton flavor violation channel, and the standard model doesn't produce many or any signals that are similar, so the background from the standard model is lower as well in this case. So this right here is and this point is the maximum bound that we get. So let me unzoom here. They produced these graphs for a variety of cases, 14 TeV and 15 inverse autobarns, but in all cases is the same. This lower part here is stronger bounds than this lower part, considering the electrons, and this this corner has the strongest bounds because of the reasons that I said earlier. So in this paper, it's basically it. They also talk a little bit about the photon-photon fusion, which is another case scenario for the production of the doubly charged scalar. But they just they doesn't put all of the analysis again. They doesn't remake all of the analysis again. For this case, they just put the linear bounds here in this table 1. So I think it says here, but basically for the high luminosity LHC, if we don't consider photo-photon fusion, these bounds are around 2 TeV, just something TeV. And for the high energy LHC, it's between a 3 TeV something. But if you consider photon-photon fusion, we increase the production cross-section as we are considering another process. So in this case, just to be clear, we are not changing the process, we are just considering one more. So it can be produced via Rao-Yan process and photon-photon fusion. And I think this photon-photon fusion, because in some other paper that I saw, it can be considered like I will put in the. They consider both of these cases photon-photon fusion. So these are the photon, and these are the where here you have also. So they consider this as well, but this is a T channel, and they said that they didn't want. Oh, these are some. Wait. Okay. So, considering a T channel, this will be model dependent, because here we can't consider the narrowing approximation anymore, because the width will be narrow. It's the contrary word for narrow. Large? Wide, thank you. It will be wider, so we have to do shape analysis, and so it will depend on the model. So I think what they consider here is photon-photon fusion is just this case. That to be clear, I don't know much about these processes. Just because they made clear that this would be model dependent, and they didn't decide. So I think it's just this one. And the Rao-Yan was the one that I showed previously. So, as I said, here they say that the production cross-section will increase almost 60%, and then we have these stronger bounds, like scaling to 1 TeV more. And it's basically this. It's more of a grayscaling than model analysis or anything, just to be put the lower bounds on the expectation for the next results for LHC, high luminosity, and high energy. So it's not too much theoretical. And yeah, it's basically this.
Let's go into the Leticia.
Hi.
Anyone has any question?
Oh wait, my face is. Sorry.
I think you comment about a theoretical bound. What is that theoretical bound you mentioned?
Theoretical? Oh no, it's just oh wait, where is it?
Yeah, I think it's this.
Here.
Yeah.
No, it's just the theoretical curve for the cross section.
Oh, okay.
So this, I said bound, but it's not about. The bounds are from Atlas and from LHC is the green curves.
Okay.
So this are
The prediction, something like this.
yeah, it's like up to this point, the point like from the green line up is all excluded.
Oh.
So if we consider a doubly charged scalar that decays in blah blah blah, we have the cross section going with this black line.
Oh.
So in the atlas, from the green up is all excluded. So the lower bounds in the mass is in this point where the black curve and the green curve meets.
Okay.
But if we have higher luminosity, then we exclude much more of the parameter space, and the lower bounds are now this point. So all of the black line here is excluded.
More questions? If not, let's paint this again.
Thank you.
Okay, that was for Leticia. So I'm gonna end the stream here, and then we're gonna continue with David's presentation.